This is the Recon Scanner, a deceptively powerful item that can completely turn the tide of a battle royale fight. Once the projectile is launched into the air, it reveals enemies and loot, even through walls. This gives the player a massive upper hand, allowing them to track not only the enemy's location but their every movement. Are they reloading, healing, or rotating into a new circle? But behind this effect is a surprisingly clever mix of rendering tricks, collision systems, and shader logic, all working together in real time. Welcome to Decoded, a series where we break down the tech behind iconic game mechanics. And today, we're dissecting Fortnite's scanner system. The scanner was first introduced in the form of shakedown back in Fortnite Chapter 2. When a player took down an enemy, they could shake them down to reveal the location of their teammates.
Him up off his feet, bro, and ran his pockets.
Wait, what?
This mechanic later evolved into player-controlled items like flare gun, which could scan an area and reveal nearby enemies. In the following seasons, Epic also introduced a weapon-based scanner in the form of the exotic Shadow Tracker. This item functioned as both a weapon and a utility, dealing damage while also marking enemies. There have been many more implementations of the scanner throughout the subsequent chapters, but we won't be covering all of them today. The core functionality of the scanner is quite simple. Once active, it finds enemies within a defined area and highlights them through obstacles for a short duration. It can also differentiate between different types of entities using colors and icons. However, because of how powerful the mechanic is, the devs had to design it with strict limitations. Scanned enemies are always notified when they have been detected. The scan itself only lasts a limited duration, and many scanner items are limited by quantity. So, how is a mechanic like this actually built? Before we start, it's important to note that this may not be the exact method the developers used to create the mechanic. There could be differences in implementation, but the underlying concepts are likely very similar. The system itself can be broken down into two parts: logic and visuals. We'll start by covering the logic side of the mechanic before moving on to the visual implementation. The first challenge we need to tackle is figuring out where the enemy is. To do this, games rely on fundamental systems called collisions. A collision is essentially an invisible area that can detect when another object enters or touches it. You've probably heard terms like wall collisions or hitboxes before. Those are all built using the same underlying concept. Collisions are also such an important part of game development that almost every game engine comes with a built-in collision system. Game engines also provide special triggers for collision interactions, such as collision enter or collision overlap. These events are called when something interacts with the collision volume, allowing the game to execute a specific block of code. And this is exactly where we'll be implementing the scanner logic as well. First, let's look at an example of a collision in action. Here, I have a basic ball with a collision attached to it. Whenever I enter the ball, a trigger is activated that changes its color to green. And once I leave the ball, the color changes back to red. Here's a visual representation of how that system works. The color changing logic itself is the custom code that gets executed whenever the trigger event is called. Another thing to note is that the visible sphere itself is not the collision. In most games, collisions are almost always invisible during gameplay. However, developers can use debugging tools to visualize what these collisions look like. Collisions can also take almost any shape or form the developer requires. So now we understand what collisions are. How do we know what entered our little detection bubble? Most collision triggers already provide that information. Once something enters the collision volume, the event gives us a reference to that object, which we can then use to tell it to perform certain actions. In this example, I've programmed the collision event to instruct the player character to scale up whenever they enter the sphere, and return back to normal once they leave it. So now our logic starts to look something like this. With the basics of the collisions covered, we can now move on to dissecting the actual Fortnite scanner. For this breakdown, we'll focus on a single item, the pulse scanner. Later on, we'll also take a look at other variations, like the weapon-based tracers. Pulse scanners are designed to be carried by the player and deployed onto the ground whenever needed. Once active, the scanner begins scanning its surroundings after a short delay. The logic behind the scan itself is actually pretty simple, now that we understand how collisions work. That's right, the pulse scanner spawns a collision volume and gradually scales up until it reaches max radius. During this expansion, any object that overlaps the collider gets highlighted based on its type. You can even visually see the sphere as it expands outwards in-game. Again, this sphere is not necessarily the collision itself, but it serves as a good visual feedback. After a short duration, the highlight fades away and the scan repeats periodically at a predefined interval. Okay, now let's build a simplified version in Unreal Engine. I'm not going to implement a full carry and throw mechanic here, and will instead focus mainly on the scanner itself. To start, we take our existing collider and gradually scale it up until it reaches a maximum radius. Keeping our color changing logic intact, the sphere should change color as soon as it touches the player, confirming that the collision still works correctly while scaling. Next, to manipulate the object that enters the sphere, I'm going to use the same player reference and change its color instead of its size. Now, if we place this scaling logic on a timer so that it repeats every few seconds, we essentially have a simplified pulse scanner system. But you might have noticed something interesting about this implementation. We are not actually using the exact location of any object. And that's by nature. The goal of the scanner is not to provide precise enemy coordinates, but rather to give the player additional visual information that helps them determine where the enemies are. All of this logic is handled by the scanner itself. Technically, we could place it inside the player, but that would quickly become inefficient once we start adding more types of scannable objects. Instead, the scanner simply checks for compatible objects and triggers their scan response if they support one. This makes the system very scalable. You can add new objects like treasure chests, vehicles, or even other players, and as long as they have a scan response, the system will automatically work. Now that we have covered the logic side of the system, let's move on to the visuals. Fair warning though, things are about to get a lot more technical, so bear with me. Remember when I mentioned that every scannable object needs a scan response? This is the same response that will handle, or rather trigger, the visual changes. Most of the heavy lifting for this effect comes from shaders, or materials in the case of Unreal Engine 5. Unreal Engine renders a scene through multiple render passes. You can think of these as different layers of information the engine generates before compositing the final image. Some passes store material data, others handle lighting, shadows, depth, ambient occlusion, reflections, and more. One of the most recognizable passes is the base color pass. This contains the raw color of every material before lighting and shadows are applied. The actual lighting calculations happen separately in later stages of the rendering pipeline. The pass that we are interested in is the custom depth pass. This is a separate depth buffer that Unreal Engine can render selected objects into, which makes it incredibly useful for effects like outlines, highlights, X-ray shaders, and so on. In simple terms, the effect works by comparing the custom depth against the regular scene depth. If the custom depth is greater, we paint a different color, resulting in the X-ray effect. Okay, maybe that was a very simple explanation, so let's dive a little bit deeper. During the calculation of scene depth, the engine stores the distance between the camera and the visible objects in the scene. So let's say there's a wall here and a ball behind it. In the standard scene depth, the engine measures the distance between the camera and the wall, which let's say is 5 meters. Since the ball is hidden behind the wall, the engine does not need to calculate its depth. Now let's take the custom depth pass. Remember, Custom depth is only calculated for objects that have it enabled. Everything else is ignored. So if the ball has custom depth enabled, the engine ignores the wall and instead measures the distance between the camera and the ball, which let's say turns out to be 8 meters. And since that value is greater than the distance to the wall, we can identify parts of the ball hidden behind the surface and selectively color them. To turn off the effect, we simply tell the object to turn off its custom depth rendering. Now coming to the type-based colors and symbols. This part is actually relatively straightforward. Scannable objects store information about what type of object they are, and we use that information to determine things like highlight colors and symbols. This type information can be stored in many different ways, such as tags, classes, structures, data tables, and so on. As for the symbols, a corresponding icon is usually positioned above the object. These icons remain hidden during normal gameplay and only become visible when the scan response is triggered. With that, the core design of our pulse scanner is now complete. The weapon variants of the scanner work in a very similar fashion. Instead of using a collision volume to detect enemies, the information comes directly from the weapon system itself. At its core, we are still performing a collision test, but this time we are firing a ray from the weapon. Once that ray hits the object, we simply trigger the same scan response. As for projectile-based scanners like Recon Scanner and the flare gun, you can think of their projectiles as mini pulse scanners. Once they land somewhere, the underlying logic is nearly identical. And for the medallion scanners, the player essentially becomes the center of the collision volume. So yeah, that's pretty much it. The next time you scan someone or get scanned in Fortnite, you'll know exactly what's happening behind the scenes. If you enjoyed the video or found it informative, consider leaving a like and sharing it with your gamer friends. And with that said, here's a special candy for making it till the end, and I'll see you guys in the next video.